And all right, we are now on to sensing elements. Let me check again if we have any questions. No questions, okay. I will take a quick sip of water here and we will get to sensing. Oops. Now, if you thought what we've talked about so far seemed abstract, now we get really abstract. These are the object kind of image processing algorithm type things going on here. And it's how do we even identify something as a pedestrian, a car, a cycle, so on. So here we go, be prepared. Oops, I'm not forwarding, there we go. Okay, object detection and identification. Here's another neural network issued patent, how to identify an object within a set of objects. I have, I've looked at a few of these neural networks, and what they seem to have is a first neural network, a second neural network, a third neural network, each do, or they call it a sub-neural network, numbers 1, 2, and 3, each having a particular job to do. But nonetheless, here is one of those. First neural network representing an input image, second neural network that identifies the set that's been classified as showing an object belonging to its set, and then an output score from these neural networks giving us the likelihood that the object was not shown in the first set, but it's part of the object. So that's a long, complicated way to say the object that was not in our full view is now in our full view. All right, evaluation, how to detect an object based on known structures, obtain image data of a known object appearance and of an unknown object, and determine if the unknown object is part of the known object. So once again, this goes back to where we're using, for example, the LiDAR system and sending out these point clouds and getting who knows how many signals back and trying to figure out if the signals from over here and over there are part of the same object or not. And these are ways of evaluating that. Is the first part, let's see here, where was I? It's a known object appearance, obtain image data of a known object appearance and an unknown object, and determine if the unknown object is part of the known object. So I got the front bumper before, and now maybe I have the back bumper and maybe not. All right, next one, conduct an evaluation of a first set of objects and classify the objects and determine that the environmental conditions have changed. That would be good to know. And the last one here, compare sensor data collected from an obstacle pair and determine whether the distance speed differential, the orientation differential between the obstacles exceeds a threshold and makes a determination of whether the two obstacles are actually two separate objects. So it is an interesting problem in my mind. If you have two cars going exactly the same speed, can you mistake them as a single object or not? And it looks like that is the exact problem that they are solving in many different ways. Okay. Object detection classification, how to determine the likelihood that I've categorized it correctly or incorrectly. Receive an input using a common instance neural network and generate a common instance output with an object score and likelihood. Process the input using a rare instance neural network to generate a rare instance output. So once again, two different networks doing a couple different things, and then the rarity score represents a likelihood that the input image will be incorrectly classified by the common instance neural network. That's not an issued patent, it's a 2018 publication. How to detect a vehicle in real time. Receive an image from a field of view, identify a region pair with a sliding window filter having an adjustable shape and size for first and second vehicles in first and second windows, and perform a classification of the image to determine whether the second vehicle is in the image. Next one, confidence level, how to assist in low confidence perception events. The sensor detects an object with a confidence level below a threshold. Determine a natural language question associated with the object to be displayed to a human. So then a human reviewer can hit, yes, it is a deer in the road, or no, it's not. The last one, capture, how to provide image capture with uniform illumination. So this is a image processing one. Select a range of distances from an image capture device, determine a pulse length based on a range of distances, cause the light source to generate a light pulse with a pulse length, linear decay, blah, blah, blah. In other words, there's images, they're taking things from multiple different distances, but somehow making the entire image have the same level of intensity. Okay. There's a blob in the road. What is it? There's me passing this vehicle. Is it all one vehicle? And so on. Object detection. Okay. We've detected the object. That's what we did in part 1. Now 5.2, we wanted to figure out exactly where that object is located. And here's a few ideas for that. Position and distance. Determine object position and distance by identifying an object and a ground marker if visible, and identify position information for the ground marker and determine the object or vehicle position relative to the ground marker. Next one, relative location, using known structures. Use a sensor to obtain images of an environment, identify an unobstructed region of a road, and determine whether the second region of the road has an obstruction based on comparison to the first region. And then the third one, how do I generate an object occupancy grid? Use a radar unit to identify objects by measured angle and distance and respective velocity within the object grid. So now I know where the objects are located. There's your grid. But I also need to know whether they are moving, where they are moving, how they are moving. So that's what we'll do in this section. Velocity and heading are the two categories here. How do I determine movements of an object in environment? Receive data points and select a point cloud representing an object from first and second set of points and determine a transformation between those points to determine the velocity of the object. Whew, I told you this is abstract stuff. Okay. By the way, section 6 will be exciting. It's about the user experience. So we just got to get through this section that this is where reading something yourself, these types of abstract areas, it's reading it by yourself is going to be more worthwhile than having somebody talk at you with abstract concepts. But nonetheless, we will go through these and then we'll get to the user experience. Okay. Heading, how to determine an object heading based on point cloud information. Receive LiDAR information in 3D and then determine an associated 2D projection point. Determine a set of line segments connecting two projected points. Determine an orientation of the line segment and a heading of the object based on orientation of the line segment. So putting a 3D sensing information over a 2D point and using that to predict the heading. Project the heading. How to estimate vehicle motion using reference points, identify the object and our first cloud with first points and our second cloud, and then having a transformation between the two views, estimate a projection of the reference point to determine motion characteristics of the object. And the last one, how do I determine the future heading? Identify an object in the environment, an area corresponding to the expected location of the wheel of the object based on a model of wheel locations, and then estimating an orientation of the wheel based on sensor data to determine a future heading. There's two more here on object motion. Calculate the velocity of a vehicle. Use two radar sensors, one to calculate angular velocity, the other linear velocity. And wheel motion, how do I determine if a vehicle is moving? Receive image data of a vehicle wheel section, compare first and second time-separated images, determine confidence level that the vehicle is in motion. And there is that section. All right, vehicle operation. And so now this is more staying in this abstract zone for a little while here. This is sensing that the vehicle is operating properly. So it's your vitals for your vehicle as opposed to driving trajectories and things like that. Okay. Vehicle operation error detection, how to detect propulsion and steering errors, provide an acceleration command, monitor my acceleration, compare to the commanded acceleration and determine if there's an error. Pose, how to determine the pose of my vehicle, receive initial pose data and data quality based on inertial measurements, wheel speed, and GPS. Receive second pose data and quality from a second processor. Stuck condition, how do I detect if I'm stuck? Determine the speed of the vehicle is less than a threshold. Identify a cause for the speed. Start a timer. After it expires, determine that if the cause remains, you are stuck, and send for help. Sensor validation, how to cross-validate sensor data. Determine whether a vehicle is determine whether a vehicle is present with the first sensor and a second sensor to determine whether the vehicle is in both sensory images along with a deviation value. Oh, I see. Okay, so we're trying to, so that's misworded a little bit there. So cross-validating, one sensor tells you there's a vehicle, the other sensor needs to also tell you there's a vehicle if they're both looking in the same place, or else there's a problem. Okay, I will have to change that. Object detection, how to optimize object detection performance. Use an object detection routine to compare image labels provided by sensor to labels from a reviewer and select object detection values that result in optimal object detection. So there's our training again. Vehicle operation continues. Sensor validation, detect a vehicle with two sensors, each using a bounding box and an object value, and validate by comparing dimensions detected by both sensors. Sensor adjustment, how do I adjust my sensor based on vehicle motion? Adjust the pointing direction of the sensor based on the motion of the vehicle. That's a 2019 publication. Motion detection, how to detect the motion of a vehicle. Use radar to detect a stationary scatterer in the environment and determine the likelihood that the vehicle is stationary based on that scattering returning data. Rotor position, how to determine the position of a rotor in a motor at a given time period. Rotate a rotor of the motor at a constant angular velocity, receive data from coils and sensors with non-uniform time sequence reflective of non-uniform angular positions, and correlate that to determine the position of the motor. Okay, vehicle operation. There's your cloud and sensors. Safety. Safety mechanism. How do I determine the likelihood of collision and respond? Determine a projected future location of an object and an impact point, and select an active safety mechanism that can be moved along a rail for deployment at an impact point. So they have this movable airbag that, based upon where the impact is likely to occur, the airbag has at least a portion of it that will slide over to the predetermined area to minimize damage to the internals of the car, to the passengers of the car. All right, second one here. Determine the likelihood of collision and respond. Determine a projected future location of an object and an impact point, and select an active safety mechanism that can be moved along a rail for deployment. So both of those are two different patents, but the same movable airbag concept. Okay. There's any good pictures there? No. All right. Now we have one training the vehicle to sense things and sense itself. How to test a vehicle using virtual objects. And so use a virtual object memory to provide a set of behavior plans for objects, and randomly select a behavior plan and generate simulated sensor data in combination with real sensor data, and maneuver the vehicle based on real and virtual object data. So you're putting some VR glasses on your automobile and training it that way. Second one here, neural network, issued patent, how to train a neural network. Initiate a request to generate an experience tuple, the tuple being based on the environment, candidate actions, and an immediate quality value, and then use that as input for reinforcement learning. That's an issued patent that might be worth taking a look at as well. Okay, but wait, there's more, but we're not going to talk about today. One thing I did not realize going into this is that Waymo has a pretty good proportion of their portfolio relating to the hardware of the LiDAR system itself. And I don't want to talk for another, who knows how long, 20 minutes or 30 minutes or an hour about the shape of mirrors and the spinning of coils and things like that, because even if I was reading from a script, I wouldn't be able to make it. So I will attach those patents and references as part of the appendix. You'll be able to go through them just as easily, but that will not be covered as part of my delivery portion here. You're welcome.